let's uh, do. Uh, so we will start with this uh, convection diffusion equation solutions that we were doing last session as well, and let's take it up from there. So let's see this question, this particular question. Consider advection and diffusion uh, of flux J of variable phi across the interface of control volumes grid points I and I plus 1. Okay. So after that, three statements are given, and we have to like find out which are the correct statements. So this is a very familiar setup by now. So there are two grid points I and I plus 1, and there is an interface. So it's a control volume type of setup where we are only focusing on one interface type. And what about this flux? This flux basically represents the variable that we have like rho u phi minus. So this contains two terms. One is the advection term. So this advection term flux will depend on the velocity. So u is the velocity. So based on the velocity, the direction of the flow will be determined. And the other one is like a diffusive term. So this is basically dependent on a gradient of phi, and there is a minus sign. So this is trying to reduce the any gradient that is there. So so this can go diffusion can occur both ways. So basically, if there is a discrepancy in the phi, uh, we might regard it as concentration, we might regard it as temperature distribution, or any other thing. So this variable phi, if there are gradients, this will try to smoothen out those gradients, the diffusive term. So these are the two terms which are there, because of which there is a transport of this variable phi across an interface. So, like an equation that governs this kind of behavior is basically this. So, if you remember in the beginning of our course, we had discussed about like generalized transport equations that we are going to solve. So, along with the like Navier-Stokes equation, which is the basically the momentum transport equation, and continuity, which is the mass transport equation, we may have other transport equations associated as well, like for example, energy, like the temperature, or any other species transport equations. So this is a form of the transport equation where we have dropped the unsteady term. So there is no del T here, and we have dropped any source term or the reaction term that might come in the right hand side. Uh, as well as we have simplified it to a 1D structure. We have given it a one-dimensional structure. So only two terms are there. One is the advection and the diffusion. So this is the convection equation. So advection plus diffusion, we will call it as convection. So this is convection equation, 1D and steady. So 1D steady state convection. This, if you rearrange, can also be written as we can really see if this is our J, and if this is rearranged, this repeats this. And we have already discussed control volume methods previously, where we had seen the basically the fundamental idea behind the control volume is to like divide this finite volume method is to define control volumes, small control volumes, uh, and calculate the fluxes across it, and create a balance between them. So so here we are asked a few questions about this flux. So, the first question is the non-dimensional advection flux through the interface E is given by P, uh, rho E. So what is P here? P is Peclet number. So Peclet number is nothing but like the like comparison between the amount of uh, uh, the advection and the diffusion. So this is like advection divided by diffusion. If we have a high Peclet number, that means there is very low amount of diffusion and very high advection. Whereas very low Peclet number will be very diffusion driven. So how do we arrive at this? So even if we take this particular equation that we have here uh, and try to like non-dimensionalize, so we have to non-dimensionalize this. So to try to non-dimensionalize this, uh, let's say first let us integrate it. So let us integrate this like taking this particular model. Let us integrate this. So if we try to integrate this, what will happen is we will have rho phi I plus 1 minus rho u phi, and so this is the discrete integral that we are doing like uh, gamma I plus 1 minus I. Now here we will have here we will have this rho u at I plus 1. If I divide this whole equation by gamma, then I will have uh, plus this will be phi I plus 1 is the variable that we want to find out because like it is of the it's not let's not write like this immediately. So here basically the idea is if I divide this whole equation with gamma and then integrate, then the idea becomes much clearer. So this will be rho gamma phi I. This is equal to so, so if I dx is there, but I want to like non-dimensionalize this as well. So I will define a new variable x by delta. So I will have another. You should have a 1 by delta here. I'll send the delta away here as well. Delta. So this also you have. Uh, I'm not writing the whole thing. This is I plus 1 minus I. Okay. So this is there. So these terms that we have got right now, so this particular term, this one and this one are the peculiar numbers at the two different nodes respectively, different grid points respectively. So I plus one and I. So here this is P I plus one and this is Pi. So it is asked that non-dimensional advection flux through the interface E is given by P rho E. So if I simply write J here, J is equal to this gamma del phi del x. If I write this at E, then what this will be? And if I then non-dimensionalize this, then I have to divide this by this gamma by delta. And you see, we have the Becquerel number. We have the Becquerel number. So we have what we were asked for, the P Becquerel number, right? Phi, P into phi, uh, minus this term. We can write it as y with x by delta or any other variable that we might like. So this is also at this interface. Now there are two terms here. This is not just p phi e. So p phi e minus d phi d. But what is this next term? This next term is part of the diffusion. Only the first portion is for the advection, and it is asked. So we have to find out the advection flux. The advection flux is given by p phi e. This is what we are. So this is that.
Sir, can you explain where from x by delta term came?
Yes, sure. Let me add another slide. Okay, so we have this is I, this is I plus 1. We have to find out the flux at E. So the flux is given by J. Okay, so this is the expression for flux. But now what we are doing is we are non-dimensionalizing this. Okay, so for non-dimensional, what we do, we choose some scales, right? So what we will do, we will choose a scale for the length. So this length scale, what we have chosen is this delta. So this will depend from interface to interface. Different interfaces might have different deltas as well. So here, this is the delta. We are only focusing on one interface. So that's why we are non-dimensionalizing this length. So delta is there, and that's why we are putting a delta here. So length scale we are non-dimensional. So only variable you might say is not non-dimensional is phi, but phi is the variable we are like solving for. So we will keep it as it is, and the rest of the terms we will non-dimensional. So phi is a generic term. It may be non-dimensional from to start with. Okay, so we are not bothered about phi here. Other than that, other terms we are non-dimensional. You can assume phi to be non-dimensional from the start. Okay, so now so this portion is non-dimensional. Phi is, let's assume we have assumed non-dimensional. X by delta is no, does not have that length anymore. So this gamma by delta is there. So I will simply uh, divide this with this gamma by delta. So what will happen? This is there. So this I am like this I am denoting with J star as my non-dimensionalized flux. So this I am denoting. So here I have this P phi. I can also write the PE here because this delta is also very much associated with this interface. So this is, let's say, delta E. So PE minus, so x by delta, or you may let me write. Is the doubt clear, or
Yes, sir, it's clear.
okay? All right. What is the next statement? The next statement is total flux to the interface can be written in the form of B phi I minus A phi I plus 1. So this is something we define. This is a definition. So this J star, what we do is we define it like this. So B phi I minus A phi I plus 1. Okay. So this is the definition kind of thing. So what does this signify? It signifies the amount of flux that is coming from I to I plus 1, that is B, that is characterized with B, has a coefficient of B, and whatever is going from I plus 1 back to I, it is characterized by this A. So they both may contain both our convection term as well as a diffusive term. So this expression that we had got from our fundamentals and some discretization, this expression we can boil down to this. So how we can do that? For that we have to assume some form functions. For this phi, we have to assume we can take phi e as our weighted average of this I and I plus 1 using the length. If we say this both is delta by 2, then we can take the average. Phi e can be taken as the average. I and I plus 1 average. Other than that, we can give a special weightage to any one of them. All those things can be done, and using that, we will get an expression where this particular like values, where these are expressed in terms of interface value, right? Phi e is at the interface E, and this d phi dx, this is also at the interface E. So this we can express it in discretized forms by assuming some form functions, some linear or piecewise linear or some other form functions. We can write it in terms of our grid points, phi I and phi I. Okay. So this is correct. We will be writing our flux in the form where it is represented by the grid points. So now they are asking about a relationship between this P Tekla number and B and A. So this B and A and Tekla number, there is they are asking a relation. What the relation can be? So we can derive and find out a relation, that is also fine. So is there any other way we can like try to find out if there is a relation? So right now we have not considered any boundary conditions or anything about this particular physical problem. So this much we have, what we have done without any assumption. So this statement, this particular statement is valid for all cases. This statement is valid for all cases. We have not assumed anything. So it must be definitely valid for the case where phi I is equal to phi I. So there is no variation between I and I plus 1. Let's say uh, it must be valid for that case as well. This is a special case, but it should be valid for this. So let us focus on this particular case. And focusing on this particular case will give our answer to the third point. That's why we are focusing. So if we focus on this particular case, you can see my d phi dx vanishes. Why? There is no variation. There is no variation of phi. So this must be 0. If this is 0, what am I left with? I am left with p phi e is equal to d phi I minus a phi I plus 1. Now I have already said that phi I is equal to phi I plus 1. What will be the value in the interface? What can be possibly the value of the interface? We can definitely choose a form where it is constant, or even if we choose a linear form, it doesn't matter. Our answer that we will get will be that this is also equal to the value at the interface. So if phi I plus 1 all are equal, then we have this relation where E is equal to D. Is this understood?
Yes, sir.
Okay. So, uh, so here there is some mistake. So this will be V minus A. If V minus A, then it is correct. Otherwise, this is not correct. So only 1 and 2 are correct. So third one is not correct. Okay. Let's move to the next question. All right. So this is an extension to the previous question. So here we have developed a few ideas about this A, B, and B Becquerel number. So B and A are nothing but coefficients which we have defined for our own like benefit, so that we can handle the grid points, handle this flux with the help of the grid points phi I and phi I plus 1. We are interested in finding out phi I and phi I plus 1 at the end of the day. We are not interested in the interfaces. In finite volume method, we are not interested in finding the variables at the interfaces. We find any variable that is in our expression. If we arrive at any value at the interface, we try to write it in terms of values of the neighboring grid points. That's what we try to do. So that's what B and A is helping. And what is B and A a function of? B will be a function of the clear number, and also will be a function of this delta and any other way that the form that we are assuming for phi e. So those things also it will be a function of. And primarily we are focusing on the effect of Becquerel number. So this B as a with effect of Becquerel number, and A the effect of Becquerel number on A and B that we are focusing on. Right? So that we will see here. So it is asking which of these four relations are true. So which of these are true? So here also we have the same relation, same I plus 1, and we can assume the interface as E. So first relation asks if our Becquerel number is changed to negative, then what would happen? So let's focus on this particular relation. J star is equal to D phi minus A phi plus 1. So what are the contributors of this J? J's I point is contributing. So I to I plus 1, any flux that is going. So I to I plus 1, any flux that is going. That is being multiplied with V, and whatever is coming back, that is multiplied with V. If the Peclet number is reversed, if the Peclet number is reversed, that means our advection flow has been reversed. So whatever the advection component that we had has been reversed. If that is the case, what would happen? If our magnitude is constant, then our B minus A, that still remains B. B minus A, the difference between these two values will still remain P. So if that is the case, earlier our B might have been higher than A. Next case, our A will be higher than B. But if the difference is the same, we can and our the magnitude of the clear number is also same. We can say that the flux will be just simply reversed. The flux will be reversed. So if our Peclet number has reversed, our flux will be reversed. So whatever from I plus 1 it comes to I, that will be same as B. So A for minus P, that is a reverse flow, will have B plus P. So this contains some advection plus diffusion, and this also contains advection plus diffusion. So diffusion will be like it will be the same amount for both of them. But the advection term, the advection magnitude only has reverse. So if the advection magnitude has reverse, they will just simply swap the values. Is this clear? Alright. If there is any question, like ask. Okay. What about the second one? The second one won't be true. The second one won't be true because this is simply like making the value negative. Uh, this he would imply that b plus a is equal to 0, which is not a valid statement. This is not a correct statement. What about the third option? The third option has this mod p. So we have to break it down. So we have to see when p is positive and what happens if p is negative, what happens. So if p is positive, what happens? This statement becomes bp is equal to AP. If P is positive, maximum between P and 0 will be P. So this is plus. So this simply implies that B minus A is P. This is true. We know that. We have already seen that this is true. But what happens is if P is negative? If P is negative, then BP, this will be equal to A minus P. And if P is negative, what is maximum? P or 0? 0 will be greater than P because P is negative. So this also we just now saw that this is also true. So combining these two, we can say that the third option is also true. So the first is true, the third is true. What about the fourth one? The fourth one, like same thing, but like the thing is here, if you substitute the p is positive case, you can easily see that that becomes a is equal to a plus b. So that means p is 0, which is a special case, which is not like true for all cases. This means there is only diffusion, there is no advection. So this is a special case. So this is not always. 1 and 3 are the correct options. If there is any difficulty to understand, please let me know. Okay. All right. So next statement is we have to find out in context of uh, formulation for a convection diffusion equation. We have to find out what is A when P is minus 1. When central difference scheme is applied. We have to know what is the central difference scheme, then we can proceed with this. So let us write down the expression that we had arrived at. This one. Yes, let us write this one. This is P pi E. This is P pi E uh, minus. So I am not writing x by delta. I am simply writing x. X here means x by delta. This is equal to v by minus a. So here this we would use the scheme of central difference. So here let us draw the interface. This is I plus 1 and this is I. So central difference scheme is nothing but like we take both equal. We give equal importance to both of them, both I and I plus 1. If that is the case, what will be phi e? Phi e will be simply average of this. This is phi I. What about the diffusion term? So diffusion term, it is very uh, very straightforward to actually assume like linear description of this linear description between these two things. And we also know like from our previous handling of finite volume method that we can actually choose two different form functions for two different terms. And that is perfectly fine as long as it is based on certain principle. So here we do not need that. We can simply use our linear scheme for both. So this is this. So x by delta actually we had taken. So this actually would become 1. Right? So x by delta we had taken. So this actually becomes in that case this is equal to p pi I. So what we have done basically is achieved this right hand side. So now we can simply separate out our phi I terms and phi I plus 1 terms to find out what is v and what is v. So if we separate phi I terms, we will have 1 uh, plus this gives us phi I. If I separate phi I plus 1 with a negative sign because we have a negative sign in front of a here, then what we will have 1 minus I plus 1. This is equal to d phi I minus d phi I. So here we can easily see that A is equal to this. So which is the correct option here? So if I put minus 1.5 here, uh, this this becomes 1 plus 170. 1.7. So option B becomes the correct. So here we have used the central difference for which term? For this particular. This term we have used central difference. We have given same importance to both of the terms. So next we have the same question. We have exactly the same question. We have our p value is also same, but we have to use the upwind scheme. What is an upwind scheme? So upwind scheme is basically we use for the advection term. So let us write that down in the expression. So so p phi p minus p phi d is equal to so this is the this scheme equation is actually valid for every irrespective of the scheme that we use. This will help because this is simply how we have defined it. Now, in the previous term, this phi e was taken equally from both sides. So this is I plus 1 and this is I. So in the advection case, it was taken equally from both sides. This actually makes sense for a diffusive case, but if I have an advection and if there is a flow taking place, let's say from this direction to this direction, then which value will influence the interface value? It will be definitely the upstream, right? So I value will influence the interface more if the flow direction is as shown here. If it is in the opposite direction, then I plus 1 value will be um, more uh, influential for the interface value. And that is what is upwind scheme. Upwind scheme is the like extreme of that. So basically, it whichever direction your the flow is, the advection value takes like it from this from that point. So if the flow is from I to I plus one, when the flow will be from I to I plus one when P is positive. So, so if P is positive, then the flow direction is this, then we will have phi E is equal to phi I. If P is negative, then we have phi E is equal to phi I. It will simply assign the value of the upstream uh, point to the interface because it is an advection process. Advection process, the direction is very important. So here P is negative. So P is negative, that means we will have phi E will be replaced as plus minus this we already know. This will be phi I plus 1 minus phi divided by 1. So that this is phi I minus A phi I plus So what is asked? What is asked? A value is asked. So A value, as you can see here, A value is nothing but 1 minus. So we have to take into account this minus sign is here. So this will be 1 minus. So if I put the value here, 1 minus P is this, this is 2.5. The correct. Is the concept of this upwing scheme and the central difference scheme clear?
Yes, sir. Clear.
Move to the next 2D problem. So uh, you can like try solving this problem. And meanwhile, we can take a short break and then continue. two walls here. This wall has a temperature of 50 Kelvin, and this wall has a temperature of 40. So we are also given that there is a flow direction. There is a flow direction, and we have to use an upward. So we know what to do with that information. So that information tells us which side of a grid point, the point side of importance. Because only the upwind direction or the upflow direction, the points would influence anything which is the downstream. So no downstream points can influence anything which is upstream in the upwind side. We have to use that. So, and the flow direction is at an inclination is given, and we are assuming that the grid size is uniform and we have same values of coefficient in the discretized equation. Our discretized equation will be something like this: AP by B. This will have in this case four control points. So from the east, west, and from north. But in this case, so all these coefficients first are equal. In this case, only two of the directions will be important because our flow direction is this way. So let's suppose for this particular point, only these 2 points are of importance. The other points are of no importance. So here we have to find out the temperature of this particular point. So it's pretty simple. So what we will do is we will, let's say, find out the temperature of this point. How can we do that? We know already that these points, which points are important? These 2 points. So for any 4 points, we have this as P. This is east, west, north, south. They are the other 4 points. And our flow direction is very given very conveniently. And this flow direction basically says that anything towards this particular direction is of importance. So that usually W and S. And we have been asked to take the coefficients as same, so we would say that both of these will have same amount of influence on the point P, and N and E will have no influence because they are downstream, they are downwind to the point P, so they cannot have any influence. So what we will do, we will take the west and the south points and take an average. So what is the west point here? 150. South point is 50. So 50 plus 150 is 200 divided by 2, which is 100. This point 100. Similarly, now we will move to this point. Here also we see in the west there is 150 and in the south there is 100. So we take the average. 150 plus 100 is 250 and its average will be 120. So this point will give us 120. So we have that here. This is what is answer. So upwind scheme simplifies this things a lot. If there is only like a boundary condition at one particular site, it is basically like we can propagate that particular information to the other. Let's go to the next portion. This is quick scheme. So this is another kind of scheme. It has a like big full form. Mostly, the most important thing is here the form function is quadratic. So Q in quick stands for quadratic. So we have a quadratic form function, quadratic profile function. So how this is being used? So we again, if we draw the interface, if we draw the interface, so let's say this is I plus one, this is I. That's what we have been doing so far. Let's take this, and let's take the flow direction to this. So if this is the flow direction, what does this quick scheme do? It takes the point before this I minus 1 point, and between these 3 points, there is a quadratic function defined. There is a form function defined. It uses all the values from all these, and then that is used in the governing equation. So we have in this flux we had this p phi e. So to find out this phi e, this particular uh, uh, form is used. So how we can like do this? So let's say like we can assume that this is x is equal to 0. We can assume any other point as also no problem. So if this is x is equal to 0, we have our quadratic function. Let's say a0 plus a1x plus ax square. Say this is our quadratic function. So we have f is equal f0 is equal to phi I, f1 f1 means delta here. So f1 is equal to phi I plus 1, and f minus 1, here it is minus delta. If the grid like the distance is different, that also doesn't matter. We can put that distance in a non-dimensional. This is phi I minus 1. So we have three equations and three variables. What are the variables? A0, A1, and A2. So these are the parameters that we need to find. So we can find out the parameter, and this will give us the form function. And from there, we can evaluate our f at half. So this will give us the phi, and that phi we can substitute here and find out whatever we have. Yeah. So this is what is the quick scheme. And the advantage of this is like we are doing the upwind effect. We are taking the upwind effect here. We are taking giving more importance to the upstream points than the downstream points. But we are also not like doing it very drastically as in the upwind scheme. And also this is like a has an higher order like higher order, it should have an higher order accuracy due to its quadratic form. Not necessarily, but it does have. So, so the quadratic profile is applied only to the advection term in the governing equation. This is true. So in diffusion term, we simply use the linear method because that is simple and that like satisfies all the physical demands that is asked from a diffusion term. And we can have different profile functions for different terms. So we can go ahead with the linear form in the diffusive term, and for the advection term itself, we can apply this quadratic. So the first equation will be that. The quadratic profile is applied compulsory to the advection as well as diffusive term. So this is false. That's what we discussed. It is applied only to the advection. Now, what about the third one? In order to estimate the value of the dependent variable at interface between I and I plus 1, the values of I minus 1, and I minus 2 are used. So this is not correct. We use 3 points, but that is I plus 1, I and I minus 1. We have just done that. We have found out this interface E, which is between I and I plus 1, and we have done that using I plus 1, I, and I minus 1. So this is also not. What is correct? The first one is correct. So now we are moving towards like solving the Navier-Stokes itself. Uh, like till now we were still like focusing on a transport equation which is not Navier-Stokes, because we although we were discussing about the convective term, we were not solving for velocity. It is as if our velocity has been given from somewhere, and we are using that velocity to solve another equation, another transport equation. We have not coupled that with an Navier-Stokes, and Navier-Stokes is like as if solved separately, and we have been given the velocity. But in Navier-Stokes, these same methods are difficult to use. Why? Because in this, yeah. So in this particular terms, you see P, this Beckley number is used. So this Beckley number is contains the velocity, and this and phi is a separate variable. It does not have velocity. But in case of Navier-Stokes, both this like u term here and the u term in this phi will also become u. So this will be a non-linear term, which we have to deal in a separate way. And we cannot use this particular concept that we have been using here. So let's start. So stream function vorticity method has been developed to circumvent each of the following features of Navier-Stokes. So the stream function vorticity uh, is the like the first choice method that we can use to solve an Navier-Stokes equation. It is very simple to like use method. So basically, what we have here is say, so if this is stress term. So plus some other terms might also be there. So this, if this whole equation is, we can take a curl out of this, then the equation that we will arrive will be the vorticity string function will be the equation that we use in the vorticity string function method. So what happens here? You can clearly see the first thing that happens here is we get this one. And we know if for a scalar's gradient, curl of a scalar's gradient is 0. So we remove this. And that has a big advantage, because if we try to solve Navier-Stokes in itself, then we will see that like we have four equations, four variables, that is fine. But this variable p does not have an equation of itself. It is hiding in the momentum equations. That it does not have an equation in itself. It does not have a governing equation from where we can extract its value and then like use it elsewhere. So in this particular case, we will get this will be the equation for vorticity, and we will get another equation for the stream. Uh, so we have very separate equations for both of these variables. So these are four variables, because vorticity will be a vector, like if we are working in 3D, and psi is a scalar quantity. So that is the main advantage. So Non-linearity of adjective terms, no, that doesn't go away. We still have non-linear adjective terms. The coupled nature of the solution, that is also, it does not help in any way. The equations are still coupled, and the pressure gradient source term with no governing equations for pressure. So this is what it like gets rid of. It gets rid of the pressure gradient. So it does not have any governing equations. That's why it was difficult to deal with, and got rid of. This is the fact. Okay. There is another question here. So, based on the stream function vorticity method, so the uh, yeah, so it is asked basically what is the final form of the it is asked which is the final form that we can like try to like do this exercise by ourselves. So we take the curl here. So you can simply what you can do is basically take x momentum equation, do a del del x of it, and then do a y momentum equation again, do del del y of that, and then like finally come to an equation. In this case, I think what they have done is basically used a 2D equation. So x and y only I can see here. So they have used a 2D equation, and in that case, this method can be used. So y momentum equation, you perform a del del x over it, and x momentum equation, you perform a del del y over it, and then you can subtract. Then you will get the curl. Otherwise, you can simply do the curl. That is another way. So I can probably write it down.
Sir, in a physical sense, what does taking the curl signify?
So yeah, that's a good question. Let's say we have a vector field. So what is a vector field? So we are having, so let's say, velocity. So velocity at every point, we know velocity has a value, magnitude, and also it also has a direction. So let's say it is this way at this point, this way. So at different points, it will have some different values. Now there are two things. One is when I am talking about curl, I should also talk about divergence. So, so divergence is basically if you draw a confined space. So these vectors at this particular like boundary, if they try to get out, then it is as if like there is something source here, something like energy just trying to release it. So there is a positive flux outside the confine. Okay, this is basically given by the divergence. So if you basically take this confined space and shrink it to a particular point, then the concept remains the same. So, like for example, you have your continuity equation in a incompressible form. You have grad dot d is equal. What does this mean? This means that there is no, this is a continuity equation. So this actually signifies that there is no mass being generated or mass being accumulated. So if you take any confined space, so all sides are confined, so and you integrate all the velocity coming in and going out, you will see that both of them cancel each other. So that this signifies this. So in other words, if you have something which is net going out of a confined space, then you have this gradient is positive, greater than. And if something is going inside, then your gradient is less. So this is what is this is divergence. This is divergence. But your question was not about divergence, but I thought this will be necessary uh, for the discussion. Let me add another page. Yeah. So this is divergence. What about curl? Curl is basically how much is it rotating. So again, if you have a confined space, and maybe you do not have this divergence, what we are interested in is how much is this body rotating, how much is the vector rotating, so that you will get one curl. This you already know that this cross product actually also gives a vector. So this will also actually give a vector. Why a vector? Because you also should know the axis about this. So if there is a confined space and there is a net rotation inside this confined space, and you have the axis of rotation. This is this curl's direction. So you know the right hand thumb rule basically. So that is the axis direction, and the amount it is rotating will roughly give you the magnitude of it. So if a vector is spreading out, you have divergence, or spreading out. In simple terms, you have divergence, and if something is rotating and the axis of rotation plus the axis direction is given by curl. So now you can also understand from here why gradient of a scalar. So P is not a vector, pressure is not a vector. So a scalar quantity's gradient, uh, its curl will always be zero. So from this concept only you can understand this. How? Because this P has a value over the whole domain, right? This scalar has a value over the whole domain, and you have taken a gradient of it. So this gradient will what it will describe. So which direction this has increased and which direction it has decreased. That will be described by this gradient. This can definitely have a divergence, but it cannot have a curl because it will not have any rotation. So that's why this will always be gradient of a uh, curl of a gradient will always be zero. Similarly, if you take a vector, if you take a vector and take a curl of that vector, and then take a divergence of this. this will also be was I able to clear some of your question?
Yes, sir. Yes, sir. Thank you.
Yeah. So where I was, this. So here we what we do is take the curve. So this is pretty straightforward. This will simply take. So this I am defining as curve. So here, what the second term, what I do, uh, I will have this like this is actually a larger term because I have this dot product operator. So there are two operators. I am performing this over this operator. This operator is acting, and so this is happening, right? Uh, so I am coming back to this. Uh, Curl of pressure will be zero. That's why we are doing this, and this also will like let us first of all like write this as the u grad square d, and then take a curl of it. This will eventually be boiled down to simply this. Our like last problem remains with this particular operation. So I think the best thing to do will be simply break it down and do it one by one. So v dot grad v, this is simply u. If I take the x term, uh, so u dx plus y. This is my x term. So this will be minus dt. This will not be d. This all of them will be del. Because there are multiple uh, independent variables. So all of these derivative will be partial derivative plus del del x and the y momentum. So the y momentum term will be u del v del y del x plus d del v. You will see a lot of things cancelling out of this. So here let us first do this y minus del square u del y del x. You can already see that this term will cancel. Other than that, actually this term will remain, the other term will cancel. Let's have to find out which terms we will cancel out. I think it's best that like if it is possible, you can like do it like, do it later. So finally you should get this particular. So if you take a velocity part from like outside, so everything you do not have to convert it into like the vorticity and stream function. So if you take out this part from outside, then you will have this vorticity portion. Basically, this will look exactly like a vorticity transform with uh, again your viscosity being the diffusive like parameter. So viscosity not only acts as a diffusive parameter for momentum, it also acts as a diffusive parameter for velocity. So that's an interesting take on it. And what else we have to figure out? We have to figure out the second equation. So the first equation will be this A or B, like both are the same thing. So first equation will be this. We have to figure out which of these both the equations actually hold. So we already know like U and V, the like the definition of the like the stream function definitions, and we can use our uh, like the vorticity definition. So this is equal to del u del y minus del v del x. So we can use this particular definition to find out this. Prosper. So the stream function definitions you can like put this. So u is this is minus. If you put this here, you will find that uh, this the second, first option there is a minus sign. This is simple Poisson equation. So you can see like the first equation only the dependent variable it has is the vorticity. The second equation only dependent variable it has is actually the stream function if you already know the vorticity. So this becomes a Poisson equation. You can find out with a like initial velocity you can find out the vorticity here, and then you can find out the stream function here. And from the stream function you can find out the velocities. So again, for the next step, you can again use these velocities to find out your vorticity for the next time step, and so on. So that gives a very clear-cut passage to what to do to find out what. Okay. So there are like a couple of more questions. So in this particular formulations, we have to figure out what is the way to give a boundary condition uh, in this vorticity stream function method. So, so the way it is done is like if you have a boundary, you can easily specify your stream function. That is not a problem because stream function like this can be treated like a streamline, and in streamline we know that stream function is a constant. So a stream function value can be assigned at the boundary. But what about vorticity? So vorticity is a little bit difficult to assign a value to the vorticity. So what it is generally done is for a point above, so this is the let's say grid point at the boundary and a grid point away from the boundary, a little like the next grid above the boundary, and the distance between it say is delta 1. So we take this difference delta y and then do a Taylor series expansion to find it out. So let's see how it is done. So let's say this point is 1, this point is 2. So we want to find out psi. So how we will do that? This is basically psi 1 plus our, we will use the Taylor series expansion. So Taylor series expansion, we have this delta y del z plus delta y square by square delta square and so on. So the other we will include in our error term. So this is up to delta square f. This is psi 1. What about del psi del y? So del psi del y we already know is u, velocity u. So this can be simply written as u1 delta y. What is u1? U1 is 0. So u1 is 0 at the because of the no slip boundary. So this can be eliminated. What about the second term? Second term is nothing but del u del y at one point multiplied by delta y square. So this del u del y at point 1, this can be used to formulate a vorticity uh, boundary condition. So if this del u del y will have a value, then we can formulate a vorticity condition. So let's try to isolate this portion. So the thing is, the vorticity at uh, the boundary, this will be del v del x minus del u del y, both at 1. Now del u del x at 1 will be 0. Why? Because at with respect to x, v is not varying. V is 0 because of no penetration boundary condition. V is 0 at the boundary and will be 0 for the next x as well. So there is no gradient of like in the x direction for v. So that is 0. So vorticity is basically minus of this. So that's how we can get vorticity. But we do not actually know psi 2. So psi 2 is not known. So the boundary condition for the vorticity can only be like achieved in an iterative way. We might first know the value of psi 2 from like our calculations. Then we can put this value here, get a value of psi 1, the vorticity is zeta 1, and then iterate it to get a suitable boundary condition. So let's see which of these statements are true. So it is determined through a Taylor series expansion of the vorticity about the first point next to the wall in the interior of the fluid. So Taylor series expansion of vorticity is not really the thing here. It is determined through a Taylor series expansion of stream function might be more accurate. So 2 is correct. It involves iterative procedure. That is correct. So this is Taylor series expansion of the stream function. That based on this concept that we have just now discussed, we have a problem here. So it is delta y is given, and vorticity at point 1 is given, and stream function at point 1 is given. We have to find out stream function at point 2 that we used in our calculation. So psi 2 we have to find. So psi 2 is, as we have seen, psi 1. Uh, so this will be minus uh, so psi 1 is 40 minus this is 6 into 5 into 10 to the minus 4 by 2. So this is 60 by 2, which is 30. 40 minus 30 will be equal to 10. We have an option. If there is any doubt, you can ask. So we have simply used this, nothing else. There is another similar type of problem, but here we have a slip boundary condition. So if you remember, we had what we had done is use this, and we have neglected the u term. So here in this case, we will have this slip length here. Then, so u at 1 will be equal to L del u del y. So this is L del u del y 1 delta y plus uh, delta y square by 2 del u. And obviously there is delta order of delta y cube which is neglected. We are not interested. So in this case, what is asked? We have to find out the boundary value for what is it. So we already know that this is what is the what is it. So we have to isolate it. So in that case, this is psi 1 minus psi 2, and here we have L delta y plus delta square. Let's put in the values. So this is 50 minus 20. What is the slip length given? Slip length is given as 1 millimeter. So we will put that as 10 to the minus 3, and delta y is given as 10 to the minus 2 plus this is 10 to the minus 4 by 2. So this is 10 to the minus 4 by 2. So this is nothing but 5 into 10 to the minus 5, and this is 1 into 10 to the minus 5. So here we have 30 divided by 6, and 10 to the minus 5 we can write it as 10 to the 5. So this is 5 into, this is in SI units. We have not written the units here, but like we have made sure that everything is in SI units so that our final answer is also SI units. So this is our verticity value. 5 into 10 to the power 5 centimeters. Okay. Okay, so this is what I had for today's live session, and we would be having another live session probably on Monday and again on Tuesday. Those two will be our final live sessions before you have your assessments. If you have any questions related to like today's session, you can ask. I am planning for the last live session to be kind of a summary and recap as well as any questions that is there from your side. You can also ask. It is better that you also like if you have any questions that you have prepared, you can ask on the penultimate day as well on Monday, so that it can be answered like in a better way. Okay, if there is no question, then I will end this.
Thank you, sir.